Okay, so here we are in the lab once again. And so on the agenda today is we are going to get our LED status port up and running. And so we're going to create a virtual 8-bit port in code because we're not using a full port for the LEDs. They're just pulled off of available I/O pins. So, and that's fine. I mean, that's not a big deal. There's the hardware takes precedence because the code, it's easier to change in code, to work around stuff like that in code than to redo like hardware and traces and stuff like that. So you can, you might want to like sit down and figure out to use one full port for your LEDs. I've done that before, and you can, but it's not a big priority for me. So I'm going to show you how to do a virtual port in code in using unions and structs and unions. And so then we'll see if we can light up the LEDs and get a port going. And that's the goal for today. And it sounds easy, and it might be easy, and it might not. So let's get to it. Okay, here we are. And we're going to put the LEDs on. I figured I'd show you guys the LEDs because they're a little bit different. Most of us are familiar with the through-hole LEDs. And so there's 8 LEDs that represent an 8-bit port. So the least or the most significant bit's going to be green, while all the rest of them are going to be red. That way, when we look at it and try to read the binary that's displayed, we know which way it's red. So let's do some soldering here. All right. So like I always do, I'm going to take and put a little dab of solder on each of one pad. Do the resistors. And the LED goes here. Okay. Now, we'll do the LEDs first. Work from left to right. Since I'm set up right-handed. And it's like we got 4. We got 4 LEDs in this little pack. I can pick it up. Oh, okay. Let's dump some out on here, huh? Gotta be careful because I mean any kind of little like fast movement and they launch like a rocket going to Mars. All right, so that packet's done. So we'll do these 4 and then we'll add more. All right, so this is what they look like. And the little markings go to ground. And we'll just tack them on, get them in the right orientation, tack them on. And we'll dump some flux, reflow everything nice. It looks like I'm getting a lot of solder lately for some reason. I clean my tip and it might not be tinned well enough. We'll see what happens. Might have to switch to my other tip. So I better put them in order here. Okay. There's those tacked on. Let's get 4 more on there. Like that. Almost time to order some more. Probably have to on the next board I put together. This is the hard part, getting the first part of that little plastic peeling up without causing some kind of chaos. There we go. Okay, so we need 4 more, so we'll just 1, 2, 3. Uh-oh, one just went. Those are not cheap either. So let's see what happens here. All right, so we got 1, 2. Well, let's get these on there and look for the other ones if we can find. Oh, I see them. All right, they're on the board. We got them. All right. Whoops, that's not quite how I want it. And you got to make the LEDs line up good too for looks. You don't want them going all up and down. We get them on there, and then you can adjust them later. And I already took out 8, but we only wanted 7 of those bad boys. Because this top one, at least the most significant one, is going to be green. So we'll put those back in the bag. Put that over there. And we'll pull out a green one. And there's one left in this package right here. So pull this one out. Guess I better get it down here where I can see it. Okay. Last LED right here. There we go. All right. I'd be careful with these sharp tweezers too. They will poke you in the fingers if you're not paying attention. So let's get this over here. Like this. Okay. Now, let's move this up a little bit. And we will, looks like, maybe I should adjust that light a little bit for you guys. It's not showing the green up too good, is it? All right, so that's pretty lined up. This one's got to come over a little bit. This one's got to come down a little bit. Got to come down a little bit. Not too bad. Move down farther. All right, and this one's a little bit crooked. Like that. I mean, they don't have to be absolutely perfect. You want them to look halfway decent. I mean, it's a prototype, but I mean, people might look at it like you guys are looking at this. So, you never know. It's up to you how good you want to make it. All right. So now, let's dump some flux on these bad boys. tip's a little bit dirty right there already, ain't it? That black stuff, that's got to come off. Because it'll just keep building up and then you won't be able to get your solder to stick to your tip. I think I'm already having a little bit of trouble with it. Let's move this thing around. Like that, huh? It's soldered okay. I use sandpaper on my tip, and I don't think you really should do that, but it was really built up and I couldn't get it off any other way. So we'll see if I ruin my tip or not. Seems to be okay. And you can't get these LEDs too awfully hot, or the little plastic square colored thing, the lens, gets really soft, and I think it could actually come off. All right, I don't have too much flux down on this end. All right. Yeah, the stirring up, shaking up my flux, making it thicker, and cleaning my tip, it just totally changed the way we're soldering here. But it's doing okay. That ought to work. Looks okay. So let's hit it with some alcohol before it gets crusty and hard to clean. Yeah, it didn't take very long for 8. Huh? Depends on, maybe it's longer for you guys watching it than me doing it. I don't know. I'll have to see when I review the footage. See if I get bored. If I get bored, I'll like speed it up or cut some out or something. I don't want to make it like grueling. You don't want it to be a grueling video to watch, huh? Okay, there's the beginning. Now let's do the resistors. The resistors, I was at one time earlier on using 1K, and you get a pretty bright LED, but to reduce a little bit of power consumption, I moved to a 1.5K. So I haven't 100% decided to stick with that yet, but it seems to be working okay. But we'll see how it works later. And maybe we'll change it on the next boards. Let's see, have I even opened this one up yet? No, I haven't opened that one. Let's see if get one we already started here. Looks like I got this one already. Maybe. Did I? No, I haven't started any of these yet. Got some new ones in here. Oh, there just went one. Did you see that disappear? And I didn't see where that went. So we're just going to pretend we didn't see it and pop 8 of them out on here. Maybe we'll find it. If we find it, we'll put it back in the bag. There's 2, 3, 4. 5, 6. Did I see 7? Let's see what we got out right there. All right, let's get some of them lined up on here. For some reason, my microscope camera just stopped working. It does that sometimes. I don't know what it's doing. It gets too big a file or what? I don't know. We might be getting full. Might have to delete some videos off of it. Whoop. These don't have to be perfect. You gotta like weigh if you want it to be. I just popped one. Talking and not paying attention. You have to weigh how much you want it, how good you want it to look versus how much time you want to spend on it. Well, I definitely had 8 of them out. Probably more than 8, I guess. But we got 8 right here, and that's what counts. Looks like I didn't get any solder on that pad. Missed the number 8 pad up here. Pull it down so you guys can actually see it. But actually, soldering with one eye is just not that bad once you get used to it, and it don't take very long to get used to it. So they're doing good. All right, so I'm going to spin this guy around, start back down here like that, and let's see, we'll get a little better focus. I don't know. My video's not looking too good. I changed my lighting. I don't know if I like it. What happens if I turn it off? That's not helping either. I might have to look at my settings or something. I don't like it. All right, let's get some flux on these resistors here. Looks like it was trying to stick, get plugged up. Maybe dump more than I wanted to. Oh, not good. Not good. Oh, I got that a little hot. Look at that. Did you see that? A little hotter than I expected. All right, especially with all that flux. Spin that one around like that. And then we'll do our little dance. We get some solder to stick on our tip. Yeah, it seemed to be doing pretty good. So let's just pop that guy right there like that. That one worked good. All right, let's turn it around this way then. Maybe. Make it a little bit easier. We don't have too much solder left to do on this board. A little bit. A number of parts, but not a lot of actual bulk soldering. Just our MOSFETs and our digital potentiometer. I've never worked with one of those potentiometers like that before, so that's going to be interesting. on, have to come back. Get this green one here. Okay. See if we can just kind of help that one along a little bit. Like that. That's pretty good, but you might want to get it perfect and press your luck, and then boom, you get it all messed up, lose ground. So just got to decide what you want to do, how good you want it, or how good you don't want it. Most of the time for prototype boards, if it works, and I mean it's soldered halfway decent, physically, whether it looks good or meets IPC standards, doesn't really matter. So the reason IPC doesn't like to have this much solder on it is because when you have the solder bumped up on the ends like this, over time through changes of temperature, that ball of solder on the end can pull unevenly on that chip resistor or any part, and it can cause it to crack under high changes in temperature. But none of this stuff we should have to worry about this. But when you get like 1,000 boards out in the field and they're going through whatever the customer puts them through, which you don't really know, then it can cause failures. And all of them will fail. Maybe only 1 out of 1,000 will fail, but you will have failures. As the numbers go up, you will have failures. And that's what we're worried about. But right now, for a single prototype, no. As long as it's making good electrical contact and it's physically on the board good, where it isn't causing any kind of intermittent problems, we're good. We don't care about how many out of 1,000 are going to fail in the field. Not yet. That's other design considerations. Once we get this design figured out, then if you go into production, then you have to worry about that kind of thing. Because the numbers can kill you. But just because one fails, that doesn't mean you have a bad design. It can be anything. You have to figure out what causes your failures. But that's not really in the scope of this. So let's plug in our board here and plug it into PIC kit so we can send our firmware to it, update our firmware, because technically we have firmware in there. It may not do much, but it is firmware, and it will grow in size and become more robust and harder to work with. Kind of. But yeah. So let's I'll plug in main brain here. All right. And I'll center that a little bit better for you. Yeah, you can see. So see, we have the green LED right here. So that is our most significant bit. So, and we'll go over that a little bit in more detail. But let's go to the code and create our port. So I actually found another mistake in the schematic. That sucks. Because I was looking at the LEDs, and if you look here, this one goes to RD0, but it's PMD0. We need that. That's a data bit that has to go to our 245 chip over here. So is what happened. This is 245 chip. So if we highlight bit 0 there, input 0, we see that it's not connected. Something happened and it didn't get connected, and it didn't catch it, and I didn't catch it. That's what happens when you don't double check after you do everything. So we got to fix this. So we're gonna the way it works here, so we got this highlighted. We come over here to the PCB. So it didn't put any wire on it at all, which is kind of okay because we can get a jumper wire on there and we don't have to cut anything. So we will have to come over here like this, and we're going to have to cut this wire here somewhere on the board. Let's get it highlighted. So, and we got to cut this here, and we have to move it. This one was intended on going to this one, so we'll have to move it to this one, which is RE13 will be for the LED, and this one will be RD0 here. PMD0 will be our data bus bit 0. So we'll have to change those to get our LED port working. That kind of sucks because that could be worse, but I'm gonna have to fix that. So I'll fix that and then we'll start where we left off. All right, so I added some jumpers. So we got one right here. That'll connect the LED to the new pin, the correct pin. And then over here, we have another jumper we added right here that will connect the data bus bit 0 to PMD 0, which is, we'll get into that later too, because we're going to do that probably next. Set up the data bus. But anyway, there it is. So let's get it plugged in and get it ready to write some code back to where we were trying to start at. All right. Get mainbrain plugged in. All right. Okay. Okay. So I straightened up my header part here a little bit. I mean, however you guys want to do it, that's up to you. This is just kind of like my standard thing I do. All right. So then we're going to create a virtual port for our LED port. And you can call it a debug port, LED port, or a status port, whatever you want to call it. But we'll call it here, I guess we'll call it like the LED port anyway. So first you have to define your bits. So we're going to have like LED 0 through 7 is our bits for our LED port. So then you want to do a define, and we're gonna call it LED 0. Whoops, LED 0, and we're gonna define that as the port pin related to that. So you have to go to your schematic, and we have to come down here, put our eye on, and so we're going to start with LED 0. Okay. And so that's RD12. Okay. So we come over in the code here, and we're going to define that as port D bits RD12. All right. So that's how we're going to do that. And so we have to do 8. So whoops. If you copy it, when you copy it, if you go down to this line and you copy it, then you should be able to just go down the line like that. 6, 7, 8. So we got 8. And so then we got to figure out what all that is. So I already made a list. So you see how we go to this. We go to the schematic, and we look up what pin it goes to. So pin 1 or LED 1 goes to RE6. So then this one over here is port E and RE6. Okay. And so you just go through the whole list like that. Okay. So the next one is RD10. I'll spare you going back and forth. Um, so then the next one, I think the rest of them are E's. So this one, the rest are E's. So I'm gonna pop the E's in here. All right. So this is RE7. And this is RD15. RE15, sorry. And this is 14. And this one is 13. And this one is 2. RE2. All right. Okay. So that defines which pins on the microcontroller turn on the LEDs. Oh, and I forgot to name them here. 1, 2, 3, 4, 5, 6, 7. And we also need to, just for standard purposes, to help us with the fix the width of our variables, like 8-bit, 16-bit, 32-bit. So if you include, whoa, I got my caps on there. The standard integer.h header file, that'll help us out in our code later. It's just, you can probably get away without it, but it's recommended that you do it that way. All right, so then we might as well just check, build it, make sure it's okay, and that's our data model again. But we're okay with that. Okay, so now that we got our LEDs defined, we are going to create a union. So you go type def, type define, and that just keeps you from having to specify a union every time you call it. But it's just kind of a standard way we do unions and structures too. All right. And here. And that's our union. And then we're going to name our union. And we will just call it my union for right now, because we might have unions later. Let me change that. Let's go LED port union. Okay. That describes it a little better. All right. And so inside our union, we are going to have a structure. I like to put my brackets down there, even though a lot of people, most people, in fact, like to put them on the end right here. I like to put them like this. All right, so now we got to define the bits in our structure. So it's an unsigned, all right, and we'll just call it bit 0, and then this specifies how many bits it uses. So it's in the length is 1 bit. Okay, so then we are going to want to copy that and paste in 7 more, huh? 4, 5, 6, 7. that line. So then we got to name them bit 0, 1, 2, 3, 4, 5, and 6. I didn't. I need to paste another one, don't I? All right. 1, 0, 1, 2, 3, 4, 5, 6, and 7. Okay. So that defines our bits in the structure. And then we have to name our value for the whole thing. So that is, it's an 8-bit. And this is the standard, this is from here in the standard header here. This means, this is the same as like saying character, C-H-A-R. It's an 8-bit, unsigned 8-bit value. And we'll call that the LED port value. And we might need to underscore that to break it up. All right, and maybe even one here. It's whatever you want to name it. It doesn't have to be a specific name, but it should be something that makes you understand what it actually is. All right, so this represents the full 8-bit value here. So when you say this equals 57, then that's what all of these bits will represent, a binary 57. All right. Okay. So we got our union, and so now we got to define a specific union that we're going to use. So usually you start with union, but since we use type define, it's already here technically. So we just do this right here, and then we will call it what do we want to call it? We'll just call it my union for right now. We can change that later too. All right. So now this is what we're using right here. Okay. So now we got to write a small, simple function that returns void, and we'll call it set LED port. All right. Set LED port, and it takes in our union. And we'll call it data, just to name it. It can be any name you want there. All right. Get our brackets in there. So now we got to define what we want it to do because we'll call this set LED port, and in here we'll put the value we want to write to the LED port. So we have to tell it how to handle that. Okay. So then is what we want to do is LED 0 equals our data right here, which is our union, but it's the data dot bit 0. Okay. Now, for some reason doesn't like that at all. And I have to change this. It should be LED port union here. Should like that better. Yeah. Okay. Yeah. All right. So So now we want to copy these bad boys. And that's 8. And so then we got to rename them here. Sequence. Okay. And these two to match. All right. So there's that. Okay. So we need to declare a prototype up here for our function like we have to in all C programs. All right. That'll do that, take care of that. So then we haven't set up our ports as input or output yet. So down here, after we finish all our clock setup, we have to define our ports. So we got up here, so let's just grab this real fast so we can see what we're doing here. All right, and we're just going to put this in temporarily here just so we can look at it. And so our first port is port D. Wow, I did not want to do that. Is D12, okay. RD12, all right. Equals, or not port B, it's got to be tris D. Tris D bits, that's a little bit different, so we got to hit that. Tris D12 equals 0 for output. And we got one more D. So let's get that in there. And that is D10. That's 0. So then the rest are E's. So we'll get E6 here. And, oh, too many E's. And 6, right? Equals 0. So now we can just copy this one. We know the rest are E's. I didn't work too good. Let's just copy the whole line here. 3, 4, 5, 6, 7, 8. All right. Okay. All right. So after E6, we got E7. And after E7, we have RE15. And after 15, we have 14. And after 14, we have 13. And then we have 2. Did I miss something? 12, 10. 1, 2, 3, 4, 5, 6, 7, 8. 15, 14, 13, 7, 10, 12. Oh, we got a 6. I missed the 6. All right. And then a 2. And the order doesn't matter. It's just, you might want to keep them in order to make it look more perfect. So now we don't need these and we don't want these in here. Can't have these in here. All right, so that defines them all as outputs. And then all we have to do is, we don't want to call it over and over in the loop, so we'll do it right after this. We'll turn all the LEDs on. So we want to write the value into our union, and our union is called my LED port. So my LED port dot, the full value equals, and we're going to turn them all on, so it'd be OXFF hex 255. Use hex. You could do 255, whichever way you like to do it. I like to use hex when I can, when my brain can comprehend it, and if not, then so I don't have to convert it in my head, I'll just use a decimal number sometimes. It's just the compiler doesn't matter. It don't care. All right, so then we loaded our union with the value. So then we need to set our bits, our LEDs. So then we'll call this function here of ours and put the value in it, which is my port dot LED value. Okay. So that should set our LEDs. I can't think of anything offhand we haven't done. All right, so let's make sure it can compile. Oh, it doesn't like something. LED port. Oh, I see. We don't put this in there. Let's try it again. There we go. Okay, so we almost got it. You notice that the green LED isn't lit up. So I'm pretty sure I know what that is. We have to set up that pin as check to see if it's an analog, and if it is, we have to also configure it as digital. So let's go back to our code. So if we look up here, LED 7, which is the green one, is RE2. So RE2, we got that. So I would be willing to bet if we come over here and look at our schematic at RE2, it's an analog input, also an analog input to the A to D converter. So we have to convert it by default, they're analog. So we have to configure it as digital before we configure which direction it is. So we'll come back over here to the code and we'll just slip it right in here like this. And so it's AN analog select port E and then bits dot and it's RE2. So if it's not an input, an analog input, then it won't show up in the list. So we show up as 2, which is good. Looks like we're on the right track. Then if you come over here to the data sheet, it says here that by default they're F, which is high. And that means they're analog by default. So we want to make it, this particular one, a 0 to make it a digital output or digital input, just to make it digital. That's all this does. This part switches between analog and digital. All right. So that should do it. So if we send it to mainbrain or send it to our I/O board, there we go. There we got it. Okay, so we got it going on. So this is what we want to do. Then we have to guarantee that when we write to a specific LED, that it lights up that LED. So let's add a little bit of code to make that easier. So we'll come up here and do some more definitions here. real fast. So we'll define on as 1. And we'll define off as 0. And let's get our tabs over here like that. Whoop, too many. Okay, so that way we don't have to say 0 and 1. We can just say on and off. Makes it a little simpler. All right, so then we've already defined these. So then if we come down here and we write this to off, all right, so that's going to turn all our LEDs off. All right, using that method. Now this is a different method. So we can go LED 0 equals on, okay? And that should turn on LED 0. So let's send it to the I/O board and see if it works. Yay, okay. We did it. So that's a good indication because you can have all the LEDs come on, but if they're all scrambled up, you won't know it until you do a test like this. So we're just going to go through them real fast. And LED 1. So we got 0 and 1. We'll do LED 2. All right. Then we'll do LED 3. And we got that one. LED 4. All right. LED 5 coming down the home stretch. And 2 more. LED 6. All right. And last but not least, our favorite beautiful green LED. The most significant bit in our binary number. And there we go. Okay. And that LED is kind of a little dim. We might want to just change that to a 1K resistor on it. We'll look into that. But anyway, there you go. Okay, so we had a little bit of a problem there. That kind of bums me out a little bit because I hate when I make mistakes. But I mean, that's kind of why we're here, to show how to make mistakes and how to fix them. So I mean, I guess that's good for you guys. I don't like it too much, but yeah. So I had to add a couple jumpers, wires to the board, and it's not a big deal, and it was a pretty easy fix. Um, but yeah, we got our LED port going, and that's a big deal. That gives us status, and you can use it to debug stuff and test outputs of functions and stuff, And I mean, you can go a long way with a 8-bit port. And then when you're done with your firmware, then the port can serve as status of certain things. You can use uh, an LED to do, to say, okay, I'm booted up, I'm ready to go, or you can light up an LED when there's a fault or a problem or something. Yeah, anything. I mean, the sky's the limit. It's how you want to program it, and that's what microcontrollers are all about. It's making it so you can program it how you want it and how you need it. And so then we got our port going. So the next thing, we're going to probably work on the front end We're going to get a little bit of, well, I guess the next thing would be the PMP port. That's the data port for the microcontroller. So we're going to probably configure that, and then we can send data back and forth through the SRAM. So we should be able to read and write to the SRAM and have it be have that 245 chip be transparent. So it should be able to read and write through that thing. So that's probably the next thing we're going to do in the next video. So we're going to exchange some real data, and we got to get rid of using RE4 as a heartbeat and move that to one of the LEDs maybe. And but you got to watch out, because when you start sending everything to your LEDs, then you got too many things going there, and they start conflicting and overriding each other and stuff. So yeah, that's kind of a tricky deal too. So that's get a whole nother facet of the code and stuff. So that's the beginning user interface. Those LEDs are the beginning of a user interface. Even if primitive as it is, it's a user interface. And so then, yeah, we'll get some data going and see how hard that is. So I will see you in the next video.